Yeah, welcome here at Radio Eden, and today it's talk about radiocarbon dating. First of all, how does it work, and then also what are the problems of radiocarbon dating, if any. And we're just gonna look at this, and hopefully I can sort of highlight to you a few problems we've gotten that some of the claims which are made based on radiocarbon dating are a little bit outlandish, if not outrageous, or not really valid. Okay, let's have a look. First of all, what is radiocarbon dating all about? We've got an element, and you can see this here. It's called C14. It was invented in the late 1940s, and they recognized that there is a carbon element by the name of C14, and it's not very stable, so it emits quite a bit of radioactivity as it turns back into its original element, which is N14. Normal carbon is C12, which is a stable element. C14 is unstable. The half-life time of C14 is 7,530 years, so that means, that's a number here, that means if you've got, let's say 100 elements of isotopes of C14, after 5,730 years, half of them will be gone. They'll have disappeared. Percentage in the atmosphere is very, very small. Yeah? So if you've got a cubic meter of air, then you only 0.0000765% of that is C14. So that's very, very low. So that's about 76 millionth percentage or part of that is C12. Sorry, C14. C12 is a stable brother, so that's most of the stuff which is around. What is the significance of carbon? Maybe we should ask before we take it any further. Now carbon makes up organic matter, so all organic matter is more or less made up of carbon. So that means if you look at yourself, you look at your skin, your bones, and everything, a lot of it in there is carbon. And it gets absorbed. How does it get absorbed? It gets absorbed through plants. So plants, they through photosynthesis, they pick up CO2. They use the carbon to build up the building blocks, and and in turn they release the oxygen. Yeah. But organic life, and the problem is, I mean, C12 is normally absorbed, but plants, they don't care whether the carbon dioxide they take in is based on C12 or C14. So C14 gets absorbed to pretty much about the same percentage as it is in the atmosphere. Again, the percentage is 0.0000765%. And if you sort of take a plant apart and you look for C14 inside the plant, then you would get about the same percentage in there. The next thing is, obviously, you know, the plant breathes in carbon, and it builds itself up with this stuff and maintains pretty much the same level as what you would find in the atmosphere. But when organic life dies and disintegrates, C14 will be released as well, and obviously it will not be maintained, and the amount of C14 in the plant is going to get less and less and less as it disintegrates. And if you had a bone, and that's the whole idea about this, and you kept this bone in an area which is not affected by external factors, so for example a vacuum, very dry, no bacteria, you would find that in 5,730 years the amount of C14 in the bone would be about half of what it was when the organism died. Yeah. Hope it makes sense. Okay, let's have a look how the whole cycle works. For our radio listeners, feel free to come on the YouTube channel. It's at www.edenradio.com. For our YouTube viewers, you can see the diagram here. And what we have is we've got an atmosphere above the Earth, which goes up to about to about 400 kilometers, and some people would say, oh, this is a lot of rubbish. It's not true. The weather only happens till about 20-30 kilometers, and that's right. The weather which we see happens, most of it happens within 10 kilometers of the surface of the Earth. Then the air gets very thin. Aeroplanes can go up to about maybe 20-30 kilometers. And then we've got a vast area which is between 50 and 100 kilometers where you can't have satellites. Neither can you have aeroplanes because the air is not thin enough. And then up to 400 kilometers, and that's round about there where the International Space Station flies around, you still have small particles, not many, very, very small particles, sort of floating about and orbiting the Earth. Yeah. And that's the reason why satellites, low-orbiting satellites, eventually get too much drag and they re-enter the Earth atmosphere and crash. Anyway, one of the elements which we've got up there is N14, which is nitrogen, and we then have a problem. We've got cosmic radiation. Most of it is kept off the Earth through the magnetic shield, but some of it gets through, and so neutrons are bombarding the N14. They knock off a proton, and then suddenly we have got carbon-14. Yeah, so a new element. The element is changed, but the problem is it's not very stable. Carbon-14 will turn into carbon-14 will break down, yeah, and eventually it'll turn back to nitrogen-14. Yeah. Okay, so that's the cycle of carbon-14 and of and how carbon-14 is created. Again, it's not a natural substance. It's caused through energy, and once this energy is lost, it returns to its original status and it becomes nitrogen-14 again. Goes back up in the atmosphere and goes up there. Now, it's very important to understand how this cycle is. You have to sort of bear in mind that there's a limited amount of nitrogen in the high atmosphere, so that's going up to 400 kilometers, and you also have to understand that that there's only a limited amount of radiation which is generating carbon-14, and obviously you can see straight away there's some sort of cycle which takes place. That so organic matter dies, carbon-14 turns back to nitrogen. As cosmic radiation hits the high atmosphere, nitrogen-14 turns to carbon-14, and so on. Okay, it's very important to bear this in mind. We're going to talk about this later a little bit more. It's quite important as well to understand this. I've got a few more pictures, a few more representations of the same thing I've just talked about. So we've got cosmic rays, sun rays, and so on, bombarding the high atmosphere of the Earth. They're fast-moving neutrons. Neutrons will collide with atmospheric nitrogen atoms, and they produce radioactive carbon-14. Yeah, plant life picks it up. Animals eat plants. Their body then is made up of the same carbon-14 they have absorbed. And as the animal dies, there's no more carbon-14 which goes in, so C14 is getting lost by decay, and it returns back to nitrogen-14. Okay, and then there's just one more picture, again the same thing. I found them. I thought they are sort of very good to see. And okay, we have now got this carbon-14, so that means every organism has got a certain amount of carbon-14. We can roughly estimate how much it is. We can measure it as well because there's a certain amount of radioactivity, and as these CO2 or the carbon-14 particles decay, radioactivity is released, and we can then just measure the radioactivity of an organism, the very low level of radioactivity, and then determine how much C14 is left in it. And that's a little bit where this comes from. So if there's a lot of C14 left in it, then we know it's died recently. If there's only a little bit of C14 left in it, and there's only a little bit of radioactivity left in this organism, like a bone or something, then we know it must have died some time ago, maybe 5,000 years ago, yeah, or depending what levels are still left in there. Okay, now scientists came along and they thought, oh, this is great, now we can date everything, because all we need to do is just measure the amount of C14, and then straight away we know aha, this bone is 1,000 years old, 10,000 years old, or 100,000 years old, depending on the level of C14 which we find in the bone. There are a couple of problems, and there are assumptions, again, and this is not discussed in science, and I'm just going to throw this in here. There are assumptions which are made which would greatly influence the interpretation of the data obtained from a bone. Okay, we're going to look at this in a minute. So how does the dating take place? So we take the value of C14 for current bone, yeah, so we know there's that amount of C14 in there. We take an old bone, measure the amount of C14 in that one, compared with a new one, with the level which we think should be there, and then we can look at a graph about the half-life time value, and we can then determine how old a bone may be. Okay, here we've got one of these tables. We've got a half-life time of 5,730 years, so that means we lose about half the C14 from organic matter. But you have to bear in mind that at the starting point, the level of C14 inside organic matter is very, very little anyway. So it is generally assumed that after 4 half-life times, the amount is so small that is almost immeasurable. So it's very difficult to measure it or to really ascertain whether it's there. You can see this at this curve as well. When you go right down to this level here, so that means after 28,000 years, it becomes very, very daunting to really make a statement of how old something is. It's a problem, yeah. So when evolutionists or others come along and they say, oh, it's 20 million years, 10 million years, 100,000 years, or whatever, and they base this on C14 analysis, it is more speculation than anything else. It's not real science, it's not real measuring. Obviously, if you look at the first part of the curve and you look at the decay within the first 5,000 years, it's much more precise. But again, there are, and you can sort of determine it quite a lot because of the amount of C14 which is lost within the organic matter. Nevertheless, it requires a couple of assumptions. We're going to look at them in a minute, and if these assumptions are not correct, then this whole concept falls over. Okay, I've got another table here. So we've got the half-life time, we've got 10 grams, 5 grams, 2.5 grams, and so on, yeah. It kind of illustrates, and you can see at the curve as well, so the first 5,000 years is quite a lot of loss, and then it gets a lot less, and so on. And as the curve flattens out, it becomes more and more difficult to really ascertain whether it works or not. Let's look at the problems with carbon dating. The first one, there's a lot of anecdotal evidence that things which have been dead for a year or a few days have been sent to labs for carbon dating, and some of them came up with ages of 2,000 years and more. And there's a lot of anecdotal evidence. So obviously that means they're getting it wrong, and you may be using it to I don't know, to make some prognosis, but it's a bit I don't know, it's a bit like a science which is very hard to verify, especially when you look at the number of items or the number of items where the date was known and they've been dated wrongly and they've been given several thousand years. The amount of C14 in the atmosphere is assumed to be a constant, and that's a really big problem. So scientists say, and let me just go back to the figure. We've got this here. Scientists say that this figure, this 0.0000765% of the atmospheric gases is C14. That this figure is the same all the time, and has been the same for a long time. And again, is this true? Is this not true? We don't know. It's a big problem. We just don't know. One thing we know, that the atmosphere has changed quite dramatically. When we look at Bernstein or amber, sometimes the little bubbles of air get locked into it, and when these air bubbles have been analyzed, the results were that the atmosphere, whenever the amber was created, and again that's another bone of contention, was very different to what we have today. First of all, the atmospheric pressure was about twice the size today. They've got other methods as well of finding out what the dates are. So, for example, they have got a layer, a fossilized layer, fossils in a layer in the ground. And we've got the geologist and we've got the biologist. Okay, the geologist finds this layer and thinks, oh, this is great. We find all these dinosaur bones in there. Then the biologist comes along and says, oh yeah, these dinosaurs were around 100,000 years ago, for example. I'm not sure about the exact age, but for example, 100,000 years ago. Then the geologist says, oh yeah, this layer must be 100,000 years old. And then we get along with the carbon dating, so they take some of these bones out, they look at how much C14 is left in them, and then they say, okay, even though we may not know whether they're constant or not, but we know that this bone who's been in this layer, which has been there for 100,000 years, has got that amount of C14 in there. So if I find a bone elsewhere and it's got the same amount of C14 in there, hence it must be 100,000 years old. Now the problem we've got here, it's circular reasoning from the onset. So the biologist relies on the geologist, and the geologist relies on the biologist to determine how old this layer is. Now if we have got a completely objective scientific approach, we have to say we don't know how this layer is, how old this layer is. We don't know how old these bones are. Let's have a look and see what we can find. And then the results may be totally different if you take these assumptions out. What we have is one assumption is confirmed by another assumption, which in turn confirms the first assumption. So it's like one lie backs up another lie, which then backs up the first lie. You might say that. Obviously, I'm a creationist. I don't believe the views which are put forward by evolutionists, just to make the point here. Therefore, I would not accept them regardless. Okay, but that's another story. That's another subject. Right now, we're just going to look at carbon dating. We're going to look at the problems we've got with carbon datings. Newspaper article: carbon dating might be wrong by 10,000 years. Yeah, I just stumbled across it. I thought I may stuck it in here, and that's a problem. We just don't know, because once, if you go back, yeah, you look at this curve. That's fine. Yeah, maybe up to 10,000 years might be fine as well, but when you look into periods which go back 100,000 years or more, according to this prediction, the amount of C14 which you've got available to play with is just negligible, absolutely negligible. So again, 4 half-life times, and you can forget about CO2 dating regardless. Okay, we've got the assumed equilibrium. Yeah, and we are going back to this value here. Yeah, this is a critical thing, and carbon dating stands or falls with this figure here. So if this figure is correct, and it's been correct for the last 100,000 millions of years of what evolutionists might make you believe, then yes, it can work, and it's a valid scientific method. Now the scientists, what they say, okay, just to show you how this works, and then I'm going to talk a little bit further about this. We've got a bucket with a lot of holes and different layers, and we've got a water tub, and the water tub fills water into the bucket. And as the water rises, more holes are covered by the water, and more water is leaving the bucket. And eventually you get the same water flowing out of the bucket as flows into the bucket. And when this is happening, then we've reached equilibrium. Yeah. So that means we have got the amount of water in the bucket, and it's not going to change, providing, and this is very important, providing the supply stays the same and we don't get more holes in the bucket. Otherwise the equilibrium changes. And I just want to go back to this cycle right at the beginning. So let's look at this diagram here. We get collisions with N14, with nitrogen. The nitrogen turns into C14, and the carbon-14 falls on the earth, gets absorbed by plant life. Plant life or organic life dies, rots away, CO2 is released, turns back into N14. Obviously the amount of N14 is limited, so the more it turns into C14, the less N14 is going to be there. And also the more plant life is dying, or organic life is dying, the more C14 is released back into the atmosphere, and then it changes back into N14. and eventually we come to a point that we reach equilibrium, where the level of C14 in the atmosphere is not rising anymore. So it's not rising, and it is not reducing itself either. And that's the point when we would say we've got equilibrium, and then it should stay the same. Now, some clever scientists calculated that equilibrium should be achieved in 30,000 years. Okay, and now we've got the logic coming in. So one assumption is backed up with another assumption, and so on. Now, some evolutionists believe that the world is 4.5 billion years old, so they reckon that the problem with equilibrium doesn't really exist. So that means that the C14, or the amount of C14 in the atmosphere, should not rise or sink, because we have reached equilibrium long time ago, regardless of whether it's a million years ago or a billion years ago. We should have reached it long time ago. So they never really looked at this aspect, and they just assumed that it's correct. Okay, let's have a look at some of the tables here, which I found. And this is a table in the last millennia, and it looks at the amount of C14 production. Again, where this data is coming from is another question, and how reliable it is. And we can see as well that the C14 production is linked with the solar output. We know that in the first, before the first millennium, between 500 AD and 1000 AD, Europe was very warm, for example. It's assumed that the solar output was very high, and then it dropped down, and we had a few sort of increases and decreases between 1000 and 1500 AD. And then after the 15th century, temperatures dropped down, solar activity dropped right down until about the 18th century, and then it rose sharply until we have got today's levels. And then we've had some changes as well. At the moment we think the solar output is falling down again, and so there should be a general cooling down as well. Now the carbon-14 production follows suit, and you can see there's a small latency according to this diagram, and so it goes up and down as well. So that means that when we are talking about equilibrium, that even today it will change up and down, and the amount of carbon-14 in the atmosphere will accordingly be also lower and higher in different seasons. And straight away we've got a problem. So if let's say 1,000 years ago the amount of CO2, the amount of C14 was a lot less than what it is today, so we are not looking at 76 millions, but maybe 30 millions, and then I do my CO2 testing, because the organic matter will start off with less C14 1,000 years ago than what we have today. So the dating will suggest to me that the organic matter is a lot older than it really is, maybe twice as old, 3 times as old, and with that the dating becomes quite problematic, because there's one little thing, is this value of C14 in the atmosphere, is it a constant or not? The problem is we don't really know, unless we can build a time machine. We can go back 1,000 years and then find it out. The question is, we've got Bernstein, we've got the bubbles in the Bernstein. Can't we measure it with that? So who's dating the Bernstein? It's the next question. So if I knew how old the Bernstein is, and then if I knew, let's say it's 1,000 years old, and then I drill in and I measure the amount of carbon-14, then I could determine, and I could say, okay, there should be X amount of C14 in the air bubble, but now I only find so much, so I know how much C14 is in there. But the problem is with the dating to start off with. How old is the Bernstein? Is it 1,000 years old, or is it 2,000 years, or 10,000 years old? Who tells me? Who's giving me this information? And very often what we find is, again, we come into the realm of speculation. Somebody makes a decision and says, oh yeah, biologist says we've got this little mosquito in there, locked in the Bernstein, therefore it must be 10 million years old, therefore I must have X amount of C14 left in it, and then the whole thing just turns into a mess. But the point is, we are just looking into speculative science rather than empirical science. There's been another problem as well. We had a lot of nuclear testing in the 50s and 60s, and in 1963 there was some agreement that nuclear testing should be stopped, and we find that the level of C14 has gone up quite steeply, and then since then it's been decaying gradually. So again, we've got a problem here where, for example, the blue line you see here is the assumed steady line of natural C14. This line is the line which is due to nuclear testing. So whatever we get today is going to be containing a lot more C14 than organic matter today than in olden days. Again, if I look back here, we can see sun has got a direct impact, or sun activity, or levels of activity have got a direct impact on the C14 production. And here we can see some artificial events, which again falsify potential dating using this technique. Okay, is C14 dating reliable? And that's the ultimate question. The figure of C14 in the atmosphere is estimated to be 0.000765%, and the big question is it a true constant? If it is, then yes, we can use it. If it is not, we have got a major problem, and we can't really use it as a reliable means to date something, not for long periods of time. Birch and number models suggest that the atmosphere was very different when they were formed, and it's a big thing as well. So if the pressure is a lot higher, there are going to be more particles in the atmosphere. And the question is this ratio still right? Is it still correct? This 76 millionth. Again, we don't know. And bit of a problem. Some scientists suggest that the amount of natural C14 in the atmosphere is rising. And that would suggest that the equilibrium is not yet reached. And again, the conclusion of that would be that the Earth is less than 30,000 years old. Very interesting point, and I would like to see more research in this area and also samples of research. What's happening to this figure? You know, how stable is it? Can we prove that it's either rising or it's going down? The problem is with nuclear testing and other things, it's very difficult to do this in our day and age. But again, we need to get away from assumptions and really go back to empirical science, where we measure, we test, and we draw conclusions from that. Rather, we speculate and we draw conclusions, which is happening in the scientific community today. Are there other factors in organic materials affecting the amount of C14 after centuries? Big question as well. So you have to imagine you've got organic matter. You know, a dog dies in a forest, the cadaver rots away, the bones are left over, and the bones are just lying in the ground. And now we've got leaves falling on it with C14. We have got leaves rotting away. The C14 may not disintegrate straight away, may still be in the natural cycle, and some of it may still go into the bone. And with that, again, we've got a problem through contamination of organic material, that the dating becomes quite a bit of a problem. I think one of the biggest problems was the Shroud of Turin. I'm not sure whether it's known. It's a shroud which is supposed to be 2,000 years old, and the big question is this real, or is this a fake from medieval times? They did some C14 testing by taking away some material from the shroud, from the edges, and they came up with a dating which was sometime in medieval times. And with that, you know, it was pretty much dismissed that the thing was real. Then thinking about this later on, they thought, okay, people have been touching and handling the shroud, and with that they would have potentially left organic matter there, you know, through handling the shroud at the edges and so on, and kissing it and what else people were doing in medieval days. They did some further testing for material elsewhere in the shroud, and they didn't need these days higher quantities, and they could come up with completely different dates, which go a lot further back, a lot closer to 2,000 years ago. But the point I'm trying to make is you've got the problem of contamination of bones, of organic material, especially if it is left in the open. And how do we account for that? And with this it becomes quite difficult. So it's not really the be all and end all C14. We can use it as a method to do some testing, to come up with some data. Can we rely on the data as the only indicative pointer? And my answer is probably not, because there are too many unknown factors, and one of them is we simply don't know what was the amount of C14 in the atmosphere 1,000 years ago, 2,000 years ago, 3,000 years ago, 4,000 years ago. We just haven't got a clue. Nobody really knows. Some scientists suggest that C14 dating is only reliable up to 500 to 1,000 years, assuming that the constant, or whatever C14 within the atmosphere, was a lot closer, and also assuming that there may have been less contamination of organic material throughout the ages. And then we've got the big problem, the circular reasoning for dating. We find something, we believe it to be so old, we measure the amount of C14 in there, we take something else, measure the same amount of C14, so we say it's a particular age. And again, that's not real science, that's not good science, that's speculation. The problem is speculation should be, or assumptions, hypothesis should be labeled as such, and it should not be presented as clear, unsurmountable fact. And with this, all that remains to be said is, if you hear evolutionists, coming up with millions of years for certain organic materials they found, or dinosaur bones, or human bones, or whatever, trying to discredit the biblical account, you can discount it quite easily, knowing that they don't know, and they can't know, whether C14 in the atmosphere is a constant or not. And to make the assumption, the Earth is 4.5 billion years old, therefore, and equilibrium takes 30,000 years, therefore it must be a constant. There might be slight variations going up and down depending on solar radiation, I'm sure. This is from the scientific community, the secular scientific community. I'm sure they would agree with that, but do they really know how high the C14 value was 2, 3, 4, 5, or even 6,000 years ago? And my answer is they don't. It's impossible, unless they've got some profits, which I'm sure they claim they have. Otherwise, they wouldn't come up with these these ideas. But my suggestion to them is that they are just a bunch of false prophets, of lying prophets. And one day they'll see, and they'll find out, and they will have to suffer the consequence of their lies they're spreading, and they are using to lead people astray, to lead people into a mistaken understanding of creation and of the things which are around us. Okay, I'm sure there's a lot of explosive material for you to comment. I hope it gives you a little bit of an idea how C14 dating works, but also what the problems are. And that, as a Christian and as somebody who believes in creation, you can safely discard it and say it's just a joke. You can laugh out loud and laugh at the scientists for spreading lies and pretending something is science, which isn't science. Okay, God bless, bye-bye. This is Michael Tremont here at Radio Eden.